I don't think this will be too terrible discussion. Yeah, 24 slides there. It's not bad at all. Number systems. So let's get into the different number systems we're going to use throughout our class. The rest of our class will be utilizing decimal number system. Obviously, we use that every day. But we'll also look into the binary number system, how computers are, again, representing everything in this binary language or number system. And then we'll look at another way of representing values using the hexadecimal number system. Now, what I'd like you to remember is this is much like just speaking a different language. You know, so I may call this a pen or a lapis, or, you know, does anybody know another language for representing a pen? Pencil, lapis, I think that's what it is in Spanish. And that's in Spanish. Oh, okay. Maybe I was thinking pencil, lapis. I don't know. Google. Okay. At any rate, so, you know, it's like speaking different languages. You can, you know, reference the same thing with a different word, you know, and in a different way. And that's what the number systems are. It's just a different representation of a value, a different way to represent a value. Okay, so we like to represent things using the decimal number system, but the computer is doing everything in binary. And so every decimal number, yep.
Bolígrafo is the pen, lapis is the pencil.
Okay, perfect. All right. Learned something new today then. So let's see. Oh, every decimal value can be represented in the binary number system, and every binary value can be represented as a decimal number. Likewise, we can even then use another number system called the hexadecimal number system to yet condense and represent large values using a small number of digits. So that's what I want you to keep in mind as we talk about these different number systems. They're just different ways to represent a value. And they have comparative. You can take any binary number can be has a decimal equivalent, and vice versa. So, you know, when they came up with the Internet Protocol, and they came up with a way of deciding how we're going to address all of the hosts that are part of this Internet on the networks, they all had to have unique identifiers. And they came up with an IP address composed of 32 ones and zeros. And that's how the devices were going to be representing those identifiers for each device. And so those 32 bits, 32 ones and zeros, were broken into 4 octets, 4 bytes, 4 sets of 8 bits. You can call them a byte or an octet. When we're talking about addressing, we usually refer to them as an octet. First, second, third, fourth octets from left to right. And so, you know, the electronic devices may be looking at IP addresses as strings of ones and zeros, 32-bit addresses, but you know, we like to represent things as 192.168.1.5, or, you know, some IP address in a decimal format. And we call that a dotted decimal format or representation of those 32-bit IP version 4 addresses. So let's talk a little bit then the difference between yeah, I stuck in some blank slides here on the break here. I think their slides are a little busy, so I'm just going to kind of write my own here real quick. I think it's easiest to see it and deal with it. Okay, let's talk about the base. Let's talk about the decimal number system first. Ooh, yeah, and I was going to... Let me do this quick. Okay. Okay, let's go with the decimal number system first. The decimal number system you've been working with since you were a kid. So we call that base 10 number system. And it's based on the digits 0 through 9. Now that's not necessarily why we call it base 10. The reason we call the decimal number system base 10 is because the string of digits, when you write a decimal number down, boy, I put a big one down there, didn't I? Well, that's all right. No, I don't want to go with that big. Oh, let's say I put down 1, 7, 8. Okay. When you put a decimal string of decimal digits down, each of those digits falls or has an associated positional value. And so if you were to read this off, you would say 178. This is the 100, 7 tens, 8 ones. You know, this is the ones position. This is the 10 spot, the 100 spots, the 1,000 spot, 10,000, 100,000, and so on as you move to the left. Each one of these values, positional values, is 10, base 10, raised to a power starting with the 0 power. Any number raised to the 0 power is mathematically defined to be 1. Any number raised to the first power is just the number itself. And from there, you're just multiplying the number by itself however many times, that exponent. That's why they call it base 10. The positional values are powers of 10. Base 10 raised to a power. And so the meaning of this decimal string is, 1 100, 1 times 10 squared, plus 7 times 10 to the first, plus 8 times 10 to the 0, or 178. Okay, 178. 8 ones. Does that make sense? Okay. So, that's kind of what we've been working with since we were kids, and we do this a lot. All right. Let's compare that to the binary number system. Okay, the binary number system is called base 2. And it uses just 2 digits. Digits 0 and 1. Okay, and so if we take 1, 2, 3, I'm going to go out 4, 8 positions. Maybe I did 9 there, huh? Oops. Okay. If we look at a binary number, let me go ahead and throw a string of digits down here. 1, 0, 1, 1, 0, 0, 1, 0. Let's see if I did that right. Okay, so I got a string of binary digits. Okay, again, these digits have place values, starting with, again, the ones position. But instead of the base being 10, the base is 2. And again, any number raised to the 0 power is 1, so you have the ones position on the rightmost least significant position all the time. And now, instead of multiplying by 10 to get to each positional value, you're going to be multiplying by 2. So you're going to have the next positional value is 2, or 2 to the first power, 4, or 2 squared, 8, or 2 to the third power, 16, or 2 to the fourth power, 32, that's 2 to the fifth power, 2 times itself 5 times, 64, 2 to the sixth power, and 128, 2 to the seventh power. There's 7, 2 to the seventh power is 128. There's 8 bits because you're starting with 2 to the 0 power and going through 2 to the 7th power. That's 8 bits there. All right, and so if we look at the meaning of this binary string, you know, what does it mean in terms of a decimal representation? What does this represent as far as a decimal value? We can find its decimal equivalent by, again, taking the digit times its place value and adding it to the next digit times its place value, and so on, just walking right down the line. Yep, so I did it on purpose, yeah, awesome. I wasn't sure, well, I was just doing it in my head as I went across to see, good, I got 178. Okay, so you see here, anytime you have a 1, well, that's simply 1 times the positional value. It's just the positional value. Anytime you have a 0, well, that zeroes out, you know, that bit position. So finding the decimal equivalent is just adding up your positional values that have a 1 in them. So it would be 128. There's a 1 in the 128 spot, a 1 in the 32 spot, a 1 in the 16 spot, and a 1 in the 2 spot. Okay, and Stephen already ran it through his head there, and that's 160, 176, 178. I'll put a little subscript 10 there showing base 10. So 10110010 base 2 is 178 base 10. This is another way to represent the value, one decimal value, 178. I can represent it in binary as a string 10110010. Okay? And we have a third number system, the hexadecimal number system, and that's base 16. So each of the positional values will be powers of 16 instead of 2 or 10. That's all it is. Okay? So let's go ahead and do something with hexadecimal number system. Well, do you want to convert a few numbers here? Maybe before, before we move to the hexadecimal number system. So let's say if I give you a number like 1, 0, 1, 1, base 2. What is that? Base 10. Okay. 11. Trevor, that's right. Yep, so how did you get that quick? Okay, this is the 1 spot. You got a 2 there, no 4, and an 8. So 8 plus 2 plus 1 is 11. Yeah, it's not so bad, is it? It's a lot easier than it, people make it out to be. You think, oh, this is math, well, it's not bad math. It's pretty straightforward. So if I go, let's say I go, how about if I go 1, 0, 1, 1, 1, 0, base 2. What's that, base 10? Well, you just work it the same way. I've got I have no 1, but I've got a 2. I've got a 4. I've got an 8. I've got an 8, 2, and a 4. No 16. And I've got a 32. So it's going to be 32 plus 8 plus 4 plus 2. That's 46. Base 10. Okay, not bad. Okay, and then if you're given a number like, let's say you're given 119 base 10, and you want to know what it is base 2. How do you convert a base 10 number to its base 2 equivalent? Well, you kind of walk it back the opposite way. You say, okay, I'm gonna be representing it in binary, and I'm gonna have a binary string of digits. Starting with the 1 spot, 2 spot, 4 spot, 8, 16, 32, 64. 128. I can stop listing numbers here because I've now gone beyond 119. Any number between 0 and 127 can be represented with 7 bits. If I have to use the 128 spot, it's a number at least 128 or bigger. So 119 can be represented with values smaller than, using powers of 2 smaller than 119. So once I get up to that, I see, okay, all right, I can't subtract out a 128 out of 119. The biggest power of 2 I can subtract out of there is 64. Is everybody all right with that? That's the biggest power of 2 that I can subtract out of 119. Okay, and Stephen, you said that's 55? Okay, well then what's the next biggest power of 2? Can I subtract a 32 out? Yep. Okay, and I've got 23. Okay, well, it'd be 16, so I'll take 16, and that'll leave 7. You're right. No 8. Okay, I can't take an 8 out, so I got to put a 0 up there. But I can take a 4, a 2, and finally a 1. There you go. Excellent. That's not bad. Yeah.
Awesome.
Trevor?
So you start with the biggest number you can subtract from it?
Yeah. Yeah, just go out to the biggest power of 2 you can subtract out of it and start there. And then work your way down. Any number you can't subtract out, put a 0 in that positional value and move your way down. For every number you can subtract out, put a 1 in that positional value.
Now, is binary like the regular decimal system in the sense that it's infinite, or is there a
It's infinite. Yep. Any decimal number infinitely large can be represented in a binary format. Just a really long string of ones and zeros, right? Yep. Okay, so, and we're going to get to this in a second here, but what's the largest value you can represent using 4 binary digits? What's the largest decimal number you can represent using 4 binary digits? 15. 8 plus 4 plus 2 plus 1. And it's the 16th number, 0 through 15. So you're going to see when we go, we're going to move to the hexadecimal number system. Every hexadecimal digit can be represented as a 4-bit binary number. Okay? Because a hexadecimal digit is 0 through 9, letters A through F. It's 16 values, distinct values. And we can represent that using 4 binary bits. Are you okay manipulating decimal to binary and binary to decimal? Seem pretty straightforward. It's really a straightforward process there. That
hexadecimal always really confusing.
Okay, so there are different ways to think about hexadecimal, and I think your curriculum just gives you a very straightforward manner of converting things. And so I don't think it's as confusing as maybe it's been presented in the past. So let's get to the hexadecimal number system. It's no harder than what we just did. So really, base 16 uses the digits 0 through 9. Okay, so now that's 10 digits. We need to get out 16 digits. So after we use up our numeric characters, we go to the alphabet. And you see the letter A stands for the decimal value 10. Letter B stands for the decimal value 11. C 12. D 13. E stands for the decimal value 14. And F stands for the decimal value 15. It only goes out. It's there. Yep. This is 16 digits. 16 digits. Okay, and so I'm going to write a hexadecimal number down. 1 to F. Excuse me, A to F. This is a hexadecimal number. Okay? I'll say base 16 here. And it works the same way, on the same principles as the other number systems, in the fact that this is the ones position, and it's 16 to the 0 power. This is the 16 spot. So instead of multiplying by 10 to get to each one is the decimal number system, or then multiply by 2 to get it to each positional value using binary, it's multiplying by 16 to get to each positional value. So this would be 16 to the first power. Now 16 times 16 is already a big number. That's 256. So what you're going to see is that we can represent large values using a small set of characters, digits. Okay? It's like being able to condense things very tightly. Okay? condensed notational format. Excuse me. Okay, so if we look at the decimal meaning of this, well, how did we do it before? Well, we took the digit times its place value, add it to the next digit times its place value, add it to the next digit times its place value. A times 256 plus 2 times 16 plus F times 1. Well, A is 10, F is 15, right? So 10 times 256. I kind of picked a nice one to work with. Just add a 0 on there, right? 2,560. Add 2 times 16, that's 32. And add 15 there. 15 times 1, 15. That'd be 2,607, right? Okay. Now there is a way you can go and convert backwards. I can give you a decimal number and you can find its hexadecimal equivalent. It's a little weirder to think about. So I'm going to just follow the lead of your curriculum. I used to show it and maybe I confused people before. So I noticed your curriculum now just gives you an easier way of doing it. They have you convert to binary, and then just convert the binary value to hexadecimal. There's a very straightforward, easy conversion between hex and binary. So if you want to go from decimal to hex, you just go decimal to binary, and then binary to hex. You just kind of convert it that. That's how your curriculum shows you. So let's go ahead and do this. Let's say that. So let me show you. This is the conversion from hexadecimal to decimal. You can take a hexadecimal number, and if you want to go to binary to find its binary equivalent, you just take each of the digits independent of one another and find the binary equivalent. So take A and write it as a 4-bit binary number. What does A look like in binary? 1010, because it's the number 10, right? It's 8 plus 2 is 10. What does 2 look like in binary? Two. No 8, no 4. You got a 2, no 1. That's 2, right? What would F? F is 15. Stephen got it. It's all of them are 1s. So A2F, base 16 hexadecimal, is the same as 2,607 decimal, and that's the same as 101000101111 base 2. Sure, yep.
You then erase
Oh, yeah. So if you wanted to convert this binary string, this is all one binary string. It would be 1. This is the 1 spot, 2 spot, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. Okay, and you can see here, taking 2048 is the biggest power of 2 you can take out of 2607. Yeah, the next one is 4096. Yep, to the right, to the left. Okay, so let's take and you work it the same way. If I give you 1 0 1 1 1 0. And I tell you that's base 2. What is this base 16? Okay, well, you're going to do almost the same thing, but you're going to, in reverse order, you're going to group it in groups of 4 bits. And then you're going to convert the groups of 4 bits to their hexadecimal equivalent. Okay, so you need to take, here's the thing when you're doing it. You've got to start from the right to the left. So you're going to take this, first batch of 4 from right to left. And this would be the 1 spot, 2 spot, 4 spot, 8 spot. You have 8 plus 4 plus 2. That's 12 plus 2, 14. That's 14. Okay, what is that? That's the letter E. E is 14. Okay, and now you have just a 1 0 here. Well, that's going to be the 1 spot. This is going to be the 2 spot. There's no 4 and no 8. It's blank. So this is just 2. So what is this base 16? It's 2e. Because there's a 0 in that spot. Yep. Yep. Nope, that's fine. Okay. That's it. Hexadecimal, not so bad. Yep, you can keep going, Yeah, if you wanted to, you could stick zeros, leading zeros there. If you wanted to. When you're doing this, you always have to make sure when you're converting hexadecimal to binary, it's got to be in chunks of 4. So even though this guy here, 2, can be done in 2 digits, 1 0, it's just 1 0, you got to make sure when you put it in here that you pad it with 2 leading zeros there for the 8 and 4 spot. Don't forget to use chunks of 4. It's got to go in chunks of 4. Okay? And that's it. That's converting the numbers. So if you want, an easy way is to use the calculator. The Windows calculator has that capability to convert number systems. Let me get us back here for a second. Now, I don't think I remember this. Okay, so your computers in the classroom don't have the Windows calculator installed? I don't know who, my old lab assistant who made the image, So instead of going to the Windows Store and installing the Windows calculator, I had just put in your if you're in Blackboard, I just put in the PowerShell command to install the Windows calculator without having to go through the Windows Store and all that stuff. If you want to install the Windows calculator on your machines in the classroom and you're logged into Blackboard, go to the you don't have to if you don't want to, but it's in the supplementary materials folder here. It's called PowerShell command to install Windows calculator here. Here it is. If you just copy this, okay, and you've got to start the PowerShell command as a administrator. So make sure when you start Windows PowerShell that you run it as an administrator. Okay. And paste her in there and hit the enter key. Okay, and you see it's getting the package. And it was very small, so it installs really quick. And now you'll be able to just hit calculator. Okay, and if it comes up standard, make sure to change the menu and go to your programmer view. Okay, and then you've got your number systems right up top. Okay, so if you want, as soon as you hit hex, look at how your keypad lights up, and you can start putting in numbers 0 through 9 and letters A through F. So what did we do? 2607 was the last number we did? A2F. A2F. I'm going to say A2F hexadecimal. A2F hexadecimal is decimal number 2607, and it's the octal number, base 8. We're not going to get into base 8, but it's the same process. And it's the binary number 101000. See the leading zeros there. 1101111. Same thing we just had, figured out. Okay. All right, and why are we getting into this? Well, we're going to see these numbers, and you will see them very shortly when we're addressing things. Go ahead and do a command prompt on your computer. If you hit the Windows button and type CMD for command, and give yourself an ipconfig /all. ipconfig. IPCONFIG, all one word, /all. Excuse me. And you have a variety of different either physical adapters or virtual adapters through VMware. But I'm just looking at, I'm just picking one of them here. I've got a DHCP v6 client identifier. Here's an example of an IPv6 address. Okay, and you see it represented in what number system? Hexadecimal. Okay, here's an IP version 4 address. It's represented in that dotted decimal format. Here's a example of another hexadecimal number, but this one's representing a physical address for an adapter. It's called a MAC address, or a physical address. It's a 12-digit hexadecimal number, and it's usually put in by the vendor. The manufacturer of the equipment. So you're seeing all these numbers systems in action here. And the addressing, the different kinds of addressing. So we're going to talk about IP addressing. We're going to talk about IPv4, IPv6. We'll talk about physical addressing, MAC addresses, and you'll see all the different number systems in use. And then later, we're going to get into the mechanics of taking IPv4 networks and breaking them into what we call subnetworks, subnetting. And that's where we're going to be converting and using the subnet mask in conjunction with the IP address. You're going to need to, be converting back and forth between decimal and binary and doing a binary ANDing process. We'll be doing that in class. So we'll be working with that binary number system. But the math is not any more difficult than what we just did. If you can add, subtract, and multiply by 2s, you're in good shape. That's what you got to be able to do. And that's it. Anybody have any questions? Okay, so they kind of have, they have a few slides here, and the slides aren't anything that we hadn't mostly discussed already. This is just a shot. It's maybe a little busier than the way I wanted to write it. Just write it on a white sheet so you didn't get. But this is base 10, the decimal number system, and they're just showing you how each positional value is a power of 10. And when you have a string of digits like 1, 2, 3, 4, 1,234, you have 1,000, 2 hundreds, 3 tens, and 4 ones, and it represents the value 1,234. And now they're showing you the binary number system and how it's not base 10, but it's base 2. So every positional value is a power of 2. Okay? And out 8 bits, it goes out from 2 to the 0 to 2 to the 7th, to the 1's position to the 128 positional value. And you can represent, find its decimal equivalent of any binary string, like 11 with 6 zeros behind it. Well, that's 128 plus 64, or 192. And so they're showing you that, well, if the computer's looking at an address like this in binary, well, what would it be in decimal? Well, you just convert each of these 8-bit values into their decimal equivalent. And you can see this one here is 2 plus 8, or 10. And this one's 1 plus 2 plus 8, or 11. This one's 168, and this is 192. There. And, when you convert a decimal number, you just keep subtracting out the largest power of 2 you can and recording those values, and you can convert from decimal to binary. We did all that. In the hexadecimal number system, again, base 16, here's just a nice little screenshot of the decimal values from 0 to 15. What do they look like in binary? Well, we represent them as a 4-digit binary number. And the hexadecimal equivalent is 0 through 9 and the letters A through F. And so I'd shown you this. I went to the command prompt and we did an IP config together. And you can see IP version 6 addresses, they're not 32 bits long like a IPv4 address. They're 128 bits long. They're 4 times the length. They're huge. And so we need some way to kind of compress that format. So they use the hexadecimal number system because we can represent 4 bits, binary bits, using 1 hexadecimal digit. And the way we then group them together, all those groups of 32 hexadecimal digits, we group them in groups of 4, 8 groups of 4. And each group of 4 is not called an octet, but it's called a hextet. because it's 4 hexadecimal digits. They represent 4 times 4, or 16 bits. 16 hex is a hextet. Okay, and we converted back and forth. So that's it. So not terrible. Do you have any questions?